All right, what we're going to do is we're going to work through an example problem. The same problem is worked as an example in your textbook. It's number 5.I.2, it says in my notes over here. It involves calculating an equilibrium constant for what is really the simplest chemical reaction we can do. In this case, we're going to think of it as the dissociation of hydrogen. So if I have hydrogen gas and if it's in contact with something at a high temperature, then some fraction of the hydrogen molecules will fall apart and give us hydrogen atoms. Right? There's applications for this. Hydrogen atoms are used for various things in materials processing industries and things like that. So, the slide we're looking at right now collects a variety of information that we'll be using throughout the calculation. And because the calculation is quite involved, what I'm going to do is I'm going to first calculate pieces of things and then pull those all together at the end, because that's kind of the simplest way I can break this down into things that I can actually manage to be able to write and keep track of. So to calculate a value for the equilibrium constant at 2000 Kelvin, then we're going to find the fraction of the dissociated hydrogen atoms at 2000 Kelvin and at a pressure of 2 bar. Information that I've got here, I have for the H2 molecule, I have the vibrational and rotational theta parameters, these temperature unit constants that describe the energy levels for those. We've been using those in calculating partition functions. I have the dissociation energy D0 for the hydrogen molecule there. Notice that in this case, our product is separated hydrogen atoms, right? So we want the separated hydrogen atoms to be our reference point, our zero of energy. So the products are already at zero energy. So my delta U 0M piece comes out to just be that dissociation energy for the molecule. Notice I don't have the thetas for the hydrogen atoms. That's because they're atoms, right? So they can't rotate or vibrate. They only will have translational motion available to them. Then I have the masses of the hydrogen atom and the H2 molecule there converted into kilograms, because I'm going to set everything up in SI units for this, okay? So that's my starting information. Those are things we could look up, right? This is our equation in general for the equilibrium constant, right? And so what can we say for this? It's got these n's in there, right? Remember, those are the coefficients. So nu for the H2 is going to be -1, because I have one hydrogen molecule going away. Nu for the hydrogen atoms is going to be equal to +2. Right? Because I'm forming two of those. And so the coefficient is positive for the product and negative for the reactants, okay? And then I've got the various pieces of the partition function in there, okay? So to set this calculation up, the first thing I'm going to do is I'm going to take this piece here and I'm going to pull out of there everything except for the mass, because the other pieces are all going to be the same for both the atoms and the molecules, right? That part, remember, is calculating the translational partition function. So it's going to have terms in there for both things for those, okay? So let's just calculate what this thing comes out to be, because we'll need that number later. So I'm going to do 2 pi Boltzmann's constant and the temperature all over Planck's constant squared, and I'm going to find that to the 3/2 power. Okay, so that's, let's give ourselves brackets. That's 2 pi. Boltzmann is 1.38 times 10 to the -23. That's in joules per mole per Kelvin. My temperature is 2000 Kelvin for the calculation we're doing. On the bottom, I have h squared, which is going to be an incredibly small number, of course. So that's 6.626 times 10 to the -34th, and that's in joule seconds. And that's squared, okay? And then all of this stuff is raised to the 3/2 power. If I multiply all that out, my notes tell me that I get 2.4841 times 10 to the 71st power. Right, it's going to be a giant number because it's got a 10 to the minus 68-ish kind of thing on the bottom there, right? Because we have h squared down there. If I just take the units from how they look right now, I've got what? I've got in here, I've got joules to the -1 and seconds to the -2, and those units are raised to the 3/2 power, okay? And so if I do that, it turns out those same units come out to give me, if I just reconcile those, I can get kilograms to the 3/2 and meters to the -3. Obviously, to do that, you have to break down the joule to be able to cancel the seconds part and whatnot, okay? But that should make that thing work out. The other piece that I'm going to set up here is this one, which is just kBT over my reference pressure. My reference pressure, I'm going to be, I'm just picking, I'm going to use 10 to the 5th pascals for that, right? And so, because that would be 1 bar, that's all going to be 1.38 times 10 to the minus 23rd. Again, that's in joules per Kelvin. I put moles up there on K, and that's not right, of course. As I'm about to write it again, I'm doing it again. Joules per Kelvin here. All right. And I multiply that by 2000 Kelvin. Then on the bottom, I'm using 10 to the 5th pascals, which are also newtons per square meter. For this. And so if I multiply all that out, I get 2.761 times 10 to the minus 25th. And right now I've got Newton meters from the joules. I've got meters squared from the bottom. And then I've got newtons here, right? So I put all that together, that whole thing is going to reduce to make meters cubed for this, okay? And so that gives me most of those things. Let's move on and do some additional things from there, okay? This is definitely one where if you're trying to work along with it, you almost certainly want to be pausing and cleaning up and checking for things like if I write down the wrong units like I did there, for example, as we go along. Okay, I need also in that equation, I've got the rotational and vibrational partition functions for the hydrogen molecule I'm going to need. So let's do those. Q rot for the H2. Remember, that's always equal to T, the temperature, over, I've got a sigma, which is this symmetry parameter, and I've got the theta, rotational constant. That's going to be 2000 Kelvin for T. Theta for hydrogen is 2, remember, for H2, because it's got 2 identical ends, right? So we can flip it one way or the other, and you can't tell those apart. So that means this is 2, and that parameter was 85.3 Kelvin. So the rotational partition function here comes out to be 11.723. My notes tell me. I can do the vibrational one. And that's going to be what? 1 over 1. These are just the relationships that we've looked at earlier in the chapter. E to the minus, this is theta vibration over T. And so here that gives me 1 over 1 minus E to the minus 6332 was the theta. It's relatively high for as molecules go. over 2000. Both of those have units of Kelvin, so I'm just going to leave them off since I didn't write the first one. I do that and I get 1.044. That partition function should be around 1, right? Because the theta parameter for the hydrogen molecule is 6000 Kelvin. We're only at 2000 Kelvin. That means that the significant majority of our molecules are still in the vibrational ground state for hydrogen, even at that high temperature, okay? The electronic pieces that we'll need here, there is for hydrogen, the molecule, this would be equal to the degeneracy of the ground state, right? And that's equal to 1. For the hydrogen atom, if I do the electronic piece there, that one is equal to the degeneracy of the ground state for the H atom, and that one's actually equal to 2, right? That one's equal to 2 because our hydrogen atom can be either spin up or spin down, right? So there's 2 different possibilities. We essentially have 2 degenerate states for the spin of that electron while it's in the 1s orbital. And so that gives us what we need there. The next piece I'm going to calculate is, if I flip back for a second, the exponential piece, right? So if I just look at that part out there, I'm going to get a value for that, which says e to the minus delta u. This is our delta u 0m. That's somewhat awkward notation that our text uses for this over RT. That's equal to the delta U is the dissociation energy we had up there, and that was 432. That was 432 in kilojoules per mole, which means it's 432,000 in joules per mole. And then on the bottom, I've got R, which I want to put in joules. Now I get to put per mole. My temperature is still 2000 Kelvin. All right, and if I take that and evaluate it for that piece, it says I get 5.187 times 10 to the minus 12. That's got to be unitless, right? Because I got it by taking e to a quantity, and sure enough, all the units in my my exponent. This is e to the this. Okay, sorry, e to the minus all that stuff. I didn't write the e when I wrote that down. Yeah, that's what happens when I'm following along on notes. I sort of start just getting ahead of myself and leaving things out. Okay, so that gives us a lot of the pieces that we've calculated. Okay, and let's see. If I take this one here, I've got the equation back now, and now I'm going to put in the things that we've got sorted out. Okay, so let's try and do that. This thing says I'm going to want. Remember the news. The new is what? It's 2 for the H atoms, and it's -1 for the H2. So I'm going to get H atom things squared on top, and I'm going to get H molecule things on the bottom. Okay. So that says I will have something like 2 pi m h kb t to the 3/2. Let's do this times kb t over p0. Then I would have, for the other partition functions, the only one that I have to put in a value for is the electronic one, because I don't have the other pieces there, right? That's all H atom stuff, so that's on the top and squared. On the bottom now, I'm going to have the terms for the molecule, so I'm going to have 2 pi m h2 kb times t over h squared. That's to the 3/2. I've got kb t over p0. And I've got now my Q's for the rotation. Q vibration. My electronic piece is 1. I'll write it down here just so we know we didn't forget it, but it's not going to change anything, right? And then over here, I've still got e to the minus delta u 0 m over RT. Okay. So what I'm going to do is a little bit of simplifying to get ready to load in the things that we did before. Okay. So if I take these two, I've got a KB times T over P0 here and another one there. I've got squared on top and one on the bottom. So I'm going to end up with one of those on top. So that's KBT over P0. And we have a value for that earlier. Okay. Then I've got in the 2 pi kt parts, oh, I left off h squared up here. That's a bad thing to leave off. Because that will change things dramatically if we leave that off. Okay. If I pull out the masses for this, I've got that piece essentially to the 3rd power on top because I have the 3 halves and then that's inside here. So it gets squared. And then I've got 1 3/2 power on the bottom. So I'm going to end up with this quantity to the 3 halves. So I'm going to have 2 pi. I'm going to put KBT over h squared. I've got that to the 3 halves power, right? Then I've got the masses that I took out of there. I'm going to have mass of h on the top cubed, right? I'm going to have a mass of H2 down here, and it's going to be to the 3 halves because that's just my mass of H2 from in here, which was raised to the 3 halves power. Okay. The pieces with the P naught in them, those have been taken care of because they're out in front here now, right? So I'm going to end up with what? I've got the electronic partition function here. That's squared. And on the bottom, I've got my Q rot times Q vibration. And I'm still putting times Q electronic, even though that one is 1. And then I've still got my e to the minus delta U naught molar over RT. Okay. Right now, we have values that we calculated for those various things, okay? And so let's go ahead and prepare to plop those in there, okay? So I'm going to take the values that we found, and again, you can look back through things if you need to, or if you're following along. That's all going to give me K, my equilibrium constant, equal to 2.7613 times 10 to the minus 25. That piece is in meters cubed out in front of things. Then I've got this piece, which is 2.4841 times 10 to the 71st. That's the piece from the translational part, right? That had the h squared on the bottom of it. That one is in kilograms. Kilograms to the minus 3 halves, meters to the minus 3. Okay. I can't fit much more up there. So now I'm going to just come down here and do some more. I've got a piece that is 1.679 times 10 to the minus 27 kilograms. That's the mass of hydrogen. And that was cubed. Okay, I've got a 2, which is squared, and that's the electronic partition function from the hydrogen atom. On the bottom, I've got the things from the, oh, I shouldn't have gone quite that far, but oh well. I've got the things from the molecule. So I've got 3.3477 times 10 to the minus 27 kilograms. That's the mass of the hydrogen molecule, and that's to the 3 halves power. I've got the partition function. This is the rotational partition function, 7233. The vibrational partition function was 1.044. My electronic partition function is 1. And all of this is times that piece that came from the exponential. So this is 5.187 times 10 to the minus 12. If you evaluate all that and follow them all through, it should be true that all of the units should cancel. This is an equilibrium constant, so it should be coming out without any units attached. And my notes say that when I do that, I get 2.815 times 10 to the minus 6 for my equilibrium constant for the dissociation of hydrogen at 2000 Kelvin. Does that seem like it makes sense that it's very small? Well, it's breaking hydrogen apart into atoms, right? And the fact that our vibrational partition function said that most of the H2 molecules are still in the ground vibrational state. In order to dissociate it, it's going to have gotten a significant amount of vibrational energy, right? So that seems very unlikely. So our little value seems about right. Okay. Next up, we're going to continue a little bit and we're going to figure out something. We want to look at the fraction of this that's dissociated. Okay. So if I do this, remember my reaction that I'm looking at says it's H2 in equilibrium with 2 H's. Okay. So if X is equal to the fraction of the H2 that has dissociated, this part can be a little tricky sometimes to follow. Okay. If that's true, then imagine you're doing, I should have, let me give myself this over here again. Right. So if X is the fraction dissociated, then every time if one H2 dissociates, realize it's going to make 2 H's over here, right? And so my mole fractions should end up being that Y for the hydrogen is, well, let's do this. If I said that, suppose I start off and just make this, pretend I'm doing like an ice table for an equilibrium problem, right? If I said I started with 1 and I lost X of it, right? Then over here, if I started with 0, I'm going to gain 2X. Right. And so whatever happens there, I'm going to get twice as many, I'm going to get more moles when I'm over here. Right. And so all that leads me to the conclusion that my mole fractions should be equal to the hydrogen atoms is 2X over 1 plus X, because when I get to the bottom here, I have 1 minus X and I have 2X, right? So 2X is how much H there is. 1 plus X is therefore the fraction. The Y for the H2 is equal to 1 minus X over 1 plus X, right? And that's just because the number of moles is changing as things go along. So that gets us to that 1 plus X on the bottom, okay? We can connect the mole fractions to the equilibrium constant, okay? Remember that you could say, if you wrote your equilibrium constant in terms of the mole fractions thing, then you would get, this says, I could say this is equal to the product of, say, Y sub I, the mole fraction, P over P naught, with each one of those raised to the exponent, the coefficient, right? That would give me then P over P naught to the delta nu, and then I just have the relationship here, which just leaves me, now I just have the y's left, right? If in our case, we have delta nu is equal to 1, because as we react, we go from 1 mole to 2 moles, right? So the change in nu from one side to the other is we've picked up 1 mole, okay? That gives us that K, our equilibrium constant, is equal to P over P0, YH squared over YH2, right? And we know that's equal to 2.815 times 10 to the minus 6, because that's what we found at the end of all that calculating, okay? If we take that and combine it with these mole fractions, I'm going to have to skip to yet another slide to be able to write here, I think. But let's see if we can do it here. This is equal to that. That's equal to P over P naught. And P over P naught is actually just going to be 2 for us, right? Because we're at 2 bar and our reference pressure is 1 bar. So that's going to be relatively simple. But it's this times now for the mole fraction for H, I have this expression up here. So let's take that. That's 2x over 1 plus x. Square that. Down here, I get 1 minus x over 1 plus x, because that's my mole fraction for the hydrogen molecules, right? That thing we could solve for x, and if we did that, we will get x equal to k, the equilibrium constant, over 4 p over p naught plus k, and all of that thing is raised to the 1/2 power, it says over here, okay? What does that mean? That means that my P over P naught is equal to 2 for the 2 bar case that we started off with, okay? So let's just finish this out. We're almost there. I have that my fraction dissociated is equal to the equilibrium constant, which was 2.815 times 10 to the minus 6. Over 4, which was in the equation we had. 2 is the P over P naught term, plus the equilibrium constant, which is the same number as on top there. All of that to the 1/2. That says it's the square root of 3.519 times 10 to the minus 7. Which is also equal to 5.93 times 10 to the minus 4. So that's my fraction that's dissociated. That gives me YH, the mole fraction of the hydrogen atoms, is 2x over 1 plus x. So that's equal to 2 times that number. And all of that is equal to 1.186 times 10 to the minus 3. So we do, in fact, have a still fairly small fraction dissociated, right? Which makes sense in terms of the small value for the equilibrium constant. This is not part of the example that's in the textbook, I believe, but I did this similar calculation at a higher temperature at 5,000 Kelvin. And if you're really masochistic, you could check this, I guess. But at 5,000 Kelvin, I got K up to 49.2. And in that case, it's because the exponential piece, the e to the minus delta u naught over RT, that one increases a lot, and that dominates what happens to the expression, okay? And so if I had that one, and if I didn't do the calculation for the mole fraction, I guess, but if I did, I would get a much larger mole fraction dissociated, right? Because with K equal to 49, that says I've now got significant amounts of product, which is where the hydrogen atoms are. All right, that's a fairly grisly thing to do. And so you don't need to be concerned that I'm gonna make you do that whole calculation in an exam. You should be able to follow through and kind of understand how the pieces go together. It's just a question of keeping everything straight, making sure all your units work. Obviously, there's a lot of places to be able to make a mistake in there. So if you do find yourself doing a calculation like that, just make sure you're extra careful about making sure everything is in a consistent set of units and that your numbers are all making sense. Thanks.